Last time in lecture, we were talking about using the FFT. We talked about the basic structure of FFT. And the whole idea of the FFT really is to say, if I have some differential or partial differential equation, the idea is that I can expand the function sort of basically in terms of cosines and sines. That's the fundamental premise. Now, anytime you do this, the important thing is how to calculate this. And in particular, we showed that the generic thing is that it's going to be an order n squared operation to calculate these coefficients. But the big idea with Cooley and Tukey was that this can drop down to that. Okay? Making it all of a sudden, instead of just another order n squared technique, down to something that makes it one of the fastest methods on the market. Okay? So that's the big idea. Now, let's step back a minute and say, is there anything special about what I did here? I mean, this expansion in terms of these functions, these cosines and sines, is pretty standard. It's called Fourier analysis, right? So a lot of people have heard of this. You expand any function in terms of cosines and sines. But there's nothing special about what we just did there. In particular, I could expand in any kind of set of functions, as long as there's sort of some kind of, they form a complete set. Here cosines and sines do. And in particular, what we're going to talk about today are what we call the Chebyshev polynomials. Okay, so I think what I've tried to do is you'll see two spellings of it, Chebyshev with a CH and a Chebyshev with a SH. We'll try to stick with the C. I found my notes littered with two different Chebychevs, one with an S and one with a C. But if you look in the literature, often it's referred to either way. Chebyshev polynomials. Now, they're not encountered frequently. Probably maybe this is the first time you've heard of Chebyshev. But what they are is a type of polynomial that has some special properties. And the key to this is going to be simply that for this specific example, I can make a transformation which is going to allow me to solve problems in n log n again. So this is why Chebyshev gets singled out. Okay? But again, nothing special about this type of function except for that it does go fast. But there are some other ones that you might want to consider for different problems. So for instance, here's some other special functions that you can expand a problem in. For instance, the Bessel function. The Bessel function is a really good expansion basis instead of cosines and sines when you're dealing with radial problems in 2D. This is actually where the Bessel function comes up in the first place. This is such a common problem that these solution types, people said, well, let's call them something. Let's call them Bessel functions. And then there's all this stuff known about Bessel functions. MATLAB can access Bessel functions. Okay? It's a nice expansion basis because in some sense it's the natural one for this type of problem. Lashonda Polynomials, which are really good for 3D Laplace problems. That's where they arise. So when you're in that situation, Legendre is the thing you want to think about using. Here's some more. These are kind of the more famous ones that I wanted to point out. Hermite-Gauss polynomials. Well, Hermite-Gauss comes up in Schrödinger equation with a harmonic potential. This is one of the classic problems of quantum mechanics. And so this is where this comes up, but you can think about if I have problems somewhat closely associated with this, then Hermite polynomials might be the right type of expansion basis, because in some sense, what you're really doing is you're expanding in these natural solutions to the system. Okay? So in some sense, these when you would use any of these things, let me write down the other couple more here. Spherical harmonics. For 3D problems with some kind of radial symmetry. And then finally, our Chebyshev polynomials, which we're going to do on 1D bounded domains. And so when would you use these versus cosines and sines? Well, you can always use cosines and sines, and your accuracy depends upon what? Your accuracy depends upon how many modes I use. In other words, when you solve this problem, you decide on the number of Fourier modes you're going to use. And it's always a power of 2. 2 to the some power, right? So you chop up your domain into so many points, whether it's 32, 64, 128, 256. The accuracy depends upon how many Fourier modes you're going to use to represent your solution. Now, if you take a generic function, you may need quite a number of Fourier modes. But with an FFT, it goes as fast, so you kind of go, well, okay, I can take a lot of Fourier modes because I can still solve this fairly quickly. Now, why would you want to use anything else if I can do this? Well, you might want to use some of these polynomials if, for instance, you are in a situation, for instance, with a Hermite-Gauss type situation where you say, I want to expand, because I have some problems closely associated with this, I want to expand in these polynomials. Well, why would you do that? Because this is still going to cost you, all these are going to cost you order n squared. Why would you do this versus your cosine and sine expansion of the Fffft? The reason you would do this is you say, because I'm expanding in these modes that sort of in some sense are natural to the system, maybe I can expand this and I only have to use 30 modes to get a good solution, whereas maybe over here I would have to use 256 modes to get the same kind of behavior. Why would I have to use more modes here? Because cosines and sines are so generic. They're not specific to the problem. This, in some sense, is specific to the problem, so it's going to give you a much better representation of the problem with a lot fewer modes. So the reason you would use some of these things is just simply because of that. If you can get away with a lot fewer modes to expand the problem in, still maintain your accuracy, then you're working with a lot smaller number of modes. And so maybe you win here despite the fact that this is n log n, this is order n squared, but if you can go, go quite a bit smaller in the number of modes, you're in good shape. All right, does that kind of make sense? Hopefully. So for every problem, you should think about these things. If there's some kind of natural solutions or expansion basis, you might want to take advantage of that. Now, a lot of those I think maybe people have heard about. People often have heard about Bessel functions. People have often heard about, Hermite or Lashonda. But Chebyshev is one of these ones you go, I've never heard of that one. So what's special about that one? Well, what's special about it, again, is that this is the only one of those that you can basically make a simple transformation which takes you down to an n log n problem. Okay? So, let's start talking about some of the properties of the Chebyshev. First, Chebyshev polynomials satisfy the following differential equation. There it is. So it's solved on the interval -1 to 1. Has this funny structure here with square roots of 1 minus x squared in it. Oh, and that's equal to 0. And some things to point out about this. First of all, It's a Sturm-Liouville problem. It's a very important fact. What it means, if you have a Sturm-Liouville problem, is you have some really nice properties associated with this differential equation. In particular, if you were to solve for the eigenvalues of this equation, where the eigenvalues are there, eigenvalues are real and given by this. Not only are they real, but they're ordered, just like this. So as you pick up n, here's the ordering of the eigenvalue. It goes like n squared. Okay? That's one fact. 2, eigenfunctions to this problem. Eigenfunctions, real. And the eigenfunctions are this t of n. These are my eigenfunctions to the problem. Okay? There's some orthogonality conditions associated with the eigenfunctions, which are the following. Negative 1, 1. 1 minus x squared, and negative 1/2. T of n, x, t of m, x dx is equal to pi over 2 c of n delta n m. Where this is the Kronecker delta function, so it's 1 when n equals m and 0 otherwise. And here, c0 is equal to 2 and cn is equal to 1. And finally, last thing is these eigenfunctions are complete. So, these are mathematical things. What do they mean for us when we solve something? Let's go back up to what we were talking about here. When you do a Fourier expansion, your whole idea is to say, I take a function, I expand it out in terms of cosines and sines. Okay? That's what I want to do. And the only thing I've got to calculate when I do this expansion is the a of n's. Now, when you use Chebychev, you're saying, okay, instead of expanding in terms of cosines and sine, I'm expanding out in terms of these polynomials. Same thing. Only thing you've got to figure out now is, how do I calculate the a of n's? Okay? So fundamentally, it's no different than what you're doing with cosines and sines. You're just changing the function you're expanding in. And by the way, if you were expanding in Bessel functions, or Hermite polynomials, or Legendre, all you're saying is the same thing, except you're replacing this by a Bessel function or a Hermite polynomial. And the whole thing is to calculate this. Once you calculate that, this gives us the algorithm. Now you're working with these things here, these a of n's. This is what gives you the ability to start manipulating. Okay? Now, that's our main objective, is to understand this. Here are some properties of the Chebyshev in here. So if you don't know what a Sturm-Liouville problem, no big deal. The most important thing about a Sturm-Liouville is that to find these coefficients a of n's, often what you need to do is rely on some orthogonality conditions. Could have been worse. Okay? All right. So let me plot what some of these things actually look like. The definition of the Chebyshev polynomial. Let's see here. Definition is this. T of n now this is kind of an odd way to write this thing, by the way, but this is the definition of this thing. Instead of writing x here, I've written cosine theta, but the nth polynomial is like, take this argument, if it was cosine theta, cosine n theta. Okay? So, what does this give? Well, it gives the following. T0, and let's put it back in terms of x, is equal to 1. Put in 0 there. That's going to be cosine of 0, which is 1. T1 of x is x. Think about that. Put a 1 in here. You get T1. You get cosine theta. So cosine theta, theta. So if I let cosine theta just be x, then this is x. Now it gets a little bit fancier. This is where you have to start using fancy trig rules. Think about this one here. What does this mean? T2. That means T2 cosine theta is equal to cosine 2 theta. What's cosine 2 theta? And cosine 2 theta, cosine squared theta minus sine squared theta. But isn't sine squared theta cosine squared minus 1? So this comes out to be 2 cosine squared theta minus 1, if you just use your trig rules. But now if we let cosine theta be x, what do we get? This becomes x, and this thing here becomes 2x squared minus 1. Oh, that's what I have. Okay? Now you see, you're going to have to get fancier and fancier with your trig rules. You kind of know this one off the top of your head. Usually, then what's cosine 3 theta? Does anybody remember? Probably not, maybe. So, you know, anyway. These are how you generate these higher order things. Let me write down what they are. I'm writing down the first 5 of them here. Here they are. These are your first 5 Chebyshev polynomials. You're going to expand a function in a set of these things. Okay? All right. So what do they look like? Let's plot a few of these things. All right. So -1 to 1. First of all, something to notice. With this definition, the value of t of n is bounded between 1 and -1. That's kind of nice. You now have these functions that have this nice property because it is related to the cosine to this thing. And so this is between 1 and -1. It's nice. Okay? So the first one is just T0 is just, what's your T0? Just 1. T1 is equal to x. Well, that's just a line like this. The next one is 2x squared minus 1. Okay? Well, isn't that an equation of a parabola? Not only it's a parabola that at x equals 0, it's a value of 1. Right? I'm sorry, at -1. So it goes like this. The next one is a cubic. And the cubic goes something like this. And the next one is a quartic. I have a picture of it there on the page. But you see, this is the set of functions you're going to start saying, let me expand everything in this. Okay? Now, here's the big, deep connection that makes the, yeah.
Differential equation to Tn of cos theta equal cos theta. I mean, it sounds nice, but where does it come from? Because is that how it's defined?
This is how it's defined. Yeah, so a good question. So this is, in some sense, the definition of the Chebyshev polynomial. That's just how you define the sequence of what you get. Now, if you were to make the change of variable over to here, this is a function that lives on if you think about it in terms of theta, theta lives from 0 to 2 pi, and x then goes from -1 to 1. Okay? And so if you were to make a change of variable over to this problem over here, then you'd look at a problem from 0 to 2 pi. So it's just this. I'm not sure if there's a good explanation for you here.
Is that possible to solve this differential equation?
Well, this differential equation, the solutions are.
But they are all, basically, the solution of the differential equation are all the functions that verifies f of cos theta equal cos what? Okay.
So these are all solutions to that differential equation. And they are all orthogonal through here. They all satisfy this orthogonality relationship. They're all real eigenfunctions, and the eigenvalues are m² associated with each one. So these two are intimately connected, right? You can't do one without the other. All right. Now, here is here's the major observation. On some sense, you go, well, why would I expand in this? You could ask that. Like, okay, isn't cosines and sines a lot easier? Yeah. But two issues associated with this. One, boundary conditions. And two, because these don't have periodic boundary conditions like we did before. So suppose if I wanted to solve a problem on a domain and I didn't have periodic boundary conditions, that's something a little bit more difficult. Then you'd want to use something like this. 2 is the speed issue, the n log n. Why is it n log n? Well, I'll show you. Notice that by the definition, there's this natural argument change there, even in the way we defined this function. My x was just cosine theta. And theta is on this interval for x on that interval. Okay? Now, a couple things to notice. If we consider a function f of x, well, now, you think about that, that's going to be some function f cosine theta, which is going to be some function of theta. All right, now let's take the derivative of this thing with respect to theta. So what do you get? dg d theta is equal to, then here you take the derivative of this, you have to use the chain rule, you get negative f prime times the derivative on the side, which is sine theta. Here's the observation to make about this. Theta goes from 0 to pi. What is the derivative of 0 and pi? We have a sine sitting out here. So at theta equals 0 or theta equals pi, the derivative of this thing, of some arbitrary function, is 0. So no flux boundary conditions. And then all of a sudden the light goes on in your head, like it is, just boing, going, whoa, I get it, because, look, no flux boundary conditions, and there's this cosine transformation over here. So can't I just use, in fact, a discrete cosine transform to solve this? Once you make this change of variables? And indeed you can. This is why, now notice, no flux boundary conditions, you have this definition, and notice what the n's are doing, cosine of n thetas. What was the discrete cosine transformation? What did it do? Fundamentally, what a discrete cosine transformation did is expanded things in cosines. And it did it in n log n. So you see, this Chebyshev polynomial, basically, when you transform it through this change of variable here, allows you to use a discrete cosine transform to actually solve for those coefficients. Your A of n's, right? Remember, you're going to expand now at an arbitrary function. Okay? Let's write this down. Is everybody okay with that? You're going to expand now an arbitrary function, f of x, in terms of these Chebyshev polynomials, where you've got to calculate these coefficients. This is the big deal for you to do. This is what you want to do computationally as fast as possible. Here's a theoretical representation of this. But this is what's costing you generically order n squared. But what we just did is, if you make this change of variable, what you just did is you turned it into a problem where you could use a discrete cosine transform to get this. Use your discrete cosine transform to get that. All of a sudden, you got yourself down to n log n. Now, I made the comment in class about the thing that has made the Fft just this, ubiquitous thing in the sciences because is just the speed issue. It's not because everybody knows cosines and sines. It's because when you use this cosines and sines in the Fft algorithm, basically you are going faster than anything else out there. Almost, the speed pickup you get from it is amazing. And this is why the Chebyshev polynomial, which is this obscure polynomial that nobody hears about, in computational mathematics is a very important one. Because of the speed. It brings it back to life going, hey, I know nothing about this thing over here I've never used ever in my life, but if I'm going to do some computing with some different boundary conditions besides periodic, I should know about this. Okay? Puts it on the forefront of computing. So normally when you say, and this is again a spectral technique, because again you're expanding in terms of this, and you just have to calculate these coefficients. All right.
That's way cool.
Thanks, Will. I'm glad you appreciate it. I'm not sure if my audience here does, but all right. So here we go. Now, some other properties about the Fourier Chebyshev. Two issues that are important. One, what are some of its properties? And two, how does it take care of derivatives? Remember, one of the other key things about Fourier transform was when you Fourier transformed the derivative of something, all it did is pop out an ik. And so you ended up with an algebraic system. We have to have the same kind of properties here happen to make this work. All right, some properties of the Chebyshev polynomial. First, I'm just going to write some of these down. You have a very nice relationship between an iterative scheme for generating the next polynomial. So instead of going through this procedure over here, where you go, oh, geez, do I have to know all of my trig rules to get these things? No. Starting off with T0 and T1 as functions, you can generate Tn plus 1, or T2. T2 and T3 can give you T4, and so forth. So this gives you an iterative way to get your higher Chebyshev polynomials. 2. The polynomial is bounded between 1 and -1. And you can calculate that its derivative less than n squared. Also, if you remember the graph I drew there, the polynomial at plus and minus 1 is either at 1 or minus 1. Okay? If you differentiate this thing, or the derivative at the boundary, okay, so now we're looking at the derivative of the boundary here, is equal to plus or minus 1 to the n plus p product 0 to p minus 1 like that. So you know what its boundary conditions are for any derivative. What we wrote down was just for the first derivative. You go through the first derivative, you find that this is 0. Okay? So, other thing, if n is even, in my thing, then the function is odd. If n is odd, the function is even. How do you see that? Well, just come over to here. If n is even, or did I write that down? Oh, sorry. If n is even, it's even. If n is odd, it's odd. Okay? N is even here, 0. This function is even. N is odd, odd. Even, even, odd, odd, even, even. This is important when you integrate against each other, right? One of the things that you know is that when you take these to calculate these coefficients here, you're going to have to use the fact that orthogonality, the eigenfunctions. Well, the nice thing about these eigenfunctions, especially the ones when you're mixing even and odd ones, they always go to 0. An even function times an odd function over in the interval -1 to 1 gives you an odd function which goes out to 0. Okay, so the only ones you have to worry about is an even-even or an odd-odd against each other. Okay? All right, so those are some properties. And before we get to the derivative properties, there's one last issue associated with this problem that we have to take care of. Okay? Which is, what we really want to do, solving these Chebyshev polynomials, is we want to solve it in this cosine basis. Right? We want to solve it when we make this transformation over to here. We want to solve it now on the domain of theta, which goes from 0 to pi. Now think about what that means here for a minute, because this will be all important. All right, let's draw. How do I want to do this? When x goes between -1 to 1, theta goes between 0 to pi. In fact, x is cosine theta, so let's draw that. So basically you get a cosine theta. So there's this mapping here between -1 to 1, and then cosine is going to go in that interval between -0 to pi. Okay? So this is a mapping of, you can think of, I'm actually working on this theta values that goes from 0 to pi as it goes from -1 to 1. Now here's the deal. When you do a discrete cosine transform, you break up the problem into a bunch of points, right? You say, okay, what I want to do is I want to break up theta into a bunch of evenly spaced points. So when you do that, think about what happens here under transformation. You break up theta into a bunch of evenly spaced points. So think about, this is your theta, this is a projection of it, and you're breaking up to a bunch of evenly spaced points. But you're solving in theta because you want to use a discrete cosine transformation. But wait a minute. When you come back to x, what does it say about x? How are the points distributed in x? So the reason I drew it this way is because you project this down to the x-axis. And what do you get? And over here, point being that, I don't know if I drew it very well, you get bunching of points at the edges. And in the middle, less points. In fact, I have a figure of it there, which is a little bit better. Figure 28, if you look at that. And you see, a lot of bunching of the points at the endpoints. So now when you solve this problem and you define something, you say, I want to say take a function and I want to define it on this interval -1 to 1, and then I want to project it out. So if you had a function, a Gaussian for instance, from -1 to 1, what would happen is you have a lot more points on the edges than you do in the middle. So you have to be aware of that. You get very good definition then. In other words, you get increased resolution at the edges, less in the middle. So if you have a lot of sharp stuff in the middle, you might have to take a lot more points in the middle to fill it in, and it's going to give you overkill at the boundary. However, a lot of problems are such that when you actually solve them computationally, the boundary conditions drive a lot of the dynamics. There's changes near the boundaries and stuff, and a lot of the boundary conditions affect the way the behavior gives. The boundary conditions are driving the behavior, and so you have a lot of changes near the boundary, and you know this Chebyshev is perfect for that because it puts a lot of data points there. Okay? So it's a non-uniform grid when you solve this thing. And I'm going to provide you, by the way, with algorithms to do this stuff. All right, so that's a couple key factors to this thing. And we're not going to do that much with Chebyshev in class, but mostly, or in our homeworks, mostly what I want to do is introduce this idea of the Chebyshev because you should be able to know that there's more than FFT in life. Right? FFT, you probably hopefully know that already, that there's more than FFT in life. But, you know, like in math life, specifically more in like computational math life, there's more than FFT that you can use. There are these other ideas out there, and you may have a problem where you have to use them. So just put the idea out there. You can come back to it later in life. Okay? Yeah.
What is the function we're trying to approximate is not contained between -1 and 1.
Okay. So if you don't have it, you can always scale it down that way. So what if you typically your generic problem is between some negative L and L. And what you do is you make a transformation of the variables down to -1 and 1. It's a lot like even when we do Fourier transforms, right? We're always working on a 2π interval. But that's why when you do your k values, your k vectors, you have this 2πL in front. It's the rescaling down to 2π. All right. Now, with that established, we have all these nice properties. Well, I don't know if they're nice. They're just properties of Chebyshev. There's a lot of things known about them. But again, this is like obscure math. 50 years ago, people were like, oh, here's this polynomial and here's all these properties. Who cares? And it was kept as an abstract thing. You don't really learn it in most math classes unless you just don't. I never saw it until I came to a computational class because you get this n log n speed factor going for you. So the only thing you have to figure out next then is how does this thing solve differential equations? This really is why we consider this, because now we say, okay, generically, just like the FFT, I'm going to have some, you know, some differential equation. And I want to now Chebyshev transform it. Now, when we talked about a problem like this and you FFT'd it, so you Fourier transformed it, what happened? Well, you took the FFT of this whole thing and you said, ooh, I got two derivatives. What do I do with that? Oh, that just pops out an ik squared, which came out to be, I shouldn't use k there. Let's call this alpha or something like that. Then you get this. Then you can solve for u hat and then inverse Fourier transform it. It's as easy as that. So the FFT relied on the fact that there is a very specific relationship between the derivative and the derivative of the transform and the transform itself. This is very important property when we come to talking about solving equations like this. So the Chebyshev polynomial has some similar properties as well. In particular, here's the high-level abstraction. Take some operator L acting on F, and the idea is we know we can expand this in terms of our Chebyshev polynomials. Where, by the way, let's let f of x equals so here's the big deal. What's the relationship between a of n's and b of n's? That's what you're trying to establish. When we did the Fourier transform, the relationship was if you take a derivative, you get an ik out. That gave us the relationship between the a of n's and b of n's and the cosines and sines. We have to do the same thing here. I have a function. Here's its expansion. If I take, for instance, a derivative of this function, I have a new expansion, but how does b of n relate to the a of n's I already know? Okay, so let's do that. One derivative. What happens? How does a of n relate to b of n? By here. Something like this. It's clearly not as clean as the Fourier transform. But if you take a derivative, you can find the derivative coefficients by summing up your a's in this fashion. Okay? Second derivative. I'll tell you what c of n is in a moment. Yeah, okay. So the second derivative, I think I forgot to write down what it was there. You can kind of see that in the notes. Some stuff here. Okay. This basically turns out to be a matrix multiplication. I'm going to give you this matrix. I'll give you this matrix. Actually, once you have this matrix, once you know what happens with 1D, so in other words, this here, to find the new b values, this is think of that as a vector, vectors of b. I just take it some big matrix times a. That's the point of this whole thing. If I want to find the derivative, I know what the function is. What I can do, I need to know these new b values for the derivative. I can get them from the a by multiplying them by some appropriate matrix a, whose coefficients are determined from this sum. That's it. Same thing here. Second derivative made. So this is going to be some a2. So you see it works a lot like finite difference. But I get spectral accuracy here. So that's a big important thing. And then what happens if LF is, I multiply the whole thing by x. Then your b of n is equal to cn minus 1, a of n minus 1, plus a of n plus 1 over 2. And by the way, here c naught is 2, and c of n is 0 for n less than 0, and c of n is 1 for n greater than 0. So for instance, here's some standard properties associated with these. All right, so that's the Chebyshev polynomial. And really in some sense, so what I try to do, introduce it, show what the pictures are. Couple things, the things that are most important to realize. One, there is a connection between this and the cosine transform. That allows you now to pick up tremendous speed, n log n now. Because you take your problem, you transform it over, you can now solve it n log n. A consequence of that is that you now work on a non-uniform domain. Your points are now, basically, you have a little bit higher density at the edges than in the middle. But you could solve an n log n as a consequence. 2, once you understand that aspect of it, when you want to take derivatives, you see that if I take a derivative, if I have a function, I want to take derivative, essentially, it's a mapping between this a of n to this b of n through some matrix. There's a derivative matrix. I'm going to give you this. I think we're actually going to play with it in class. I think. I can't remember exactly when, but we will. And that's going to be the most important thing. Why? Because just like the Fourier transform, there's a mapping between the derivative and the function itself, which is the ik piece. Here, that's the connection between the derivative and the function itself. And once we have this derivative matrix, we can say, give me a PDE. Oh, you need to take derivative? No problem. I have this derivative matrix. Hit it with it, and then I expand everything in terms of these Chebyshev polynomials. Okay? It's just another basis to work with. It allows you to consider different boundary conditions than Fourier transforms does. And so it's a good thing to have in the back of your head. All right. That's it for Chebyshev. We're done for today.